All right, let's take a look at how to solve that simple first-order differential equation numerically. Now, before we go on to MATLAB, let's pause in Mathcad here and let's run the solution really quickly. It's easier to look at here. So the way Mathcad does this is you use something called a solve block, and that's what this rectangular space is up here. If you need an initial guess, it goes there, constraints go there, and the solver goes there, the actual command you use to calculate a value. Now, if there's a problem with this, is you can't make this box much smaller without it looking funny. It's one of the little quirks that they put into Mathcad Prime. But that said, this is pretty straightforward. Here, let me blow this up a little bit bigger. There we go. That's looking better. There. So you can see under constraints here, there's the definition of the differential equation itself. Sorry, the definition of the differential equation itself. And here, it keeps doing this, is the initial condition. And finally, right here, ODE solve, that's the command you use in Mathcad to solve ordinary differential equations. Now, like Mathcad, it's got a couple of different solvers, and I'm going to skip over the details of that just because this one's working fine. I don't know which one this is. It's probably Runge-Kutta. And you can see there's the answer right there. So what we're doing is we're defining this differential equation that, again, is numerically not well conditioned, setting the initial condition, and solving. So y prime of t equals this stuff here. There's y prime of t right there. And there's my range. It's going to go from 0 to 5 and store the result in y. And so I have t down here. Can't really see it. There it is. I guess it's over there. There's y of t. And there's the solution. It looks fine. Now, the nice part about Mathcad is this is a live document. I can change things and it'll recalculate automatically. So instead of minus 2.3, let's go to 1.5 maybe. And you can see it recalculated. What happens if I go to 1.1? That curvature should go down, I think. Yep, there it goes. And so I can go back to the original equation here and just watch it change. It's pretty cool. So there it is. We know what the solution looks like, and the syntax in Mathcad is really very straightforward. With that in mind, let's go to MATLAB. All right, here we are in MATLAB. And we're going to solve the same differential equation. We're going to do it two different ways. Now the steps are just the same. I'm going to define a range over which we're going to solve. I'm going to define initial conditions. Then I'm going to define the equation itself, and then finally solve and plot. So let's get the housekeeping out of the way. I have a variable called tspan. Now this is a vector with two elements in it. The first one's 0 and the second one's 5. That means I'm going to solve from 0 to 5. So there it is. I'm going to say y0 equals 1. So that's my initial condition. Last thing I've got to do is define the differential equation. Now the way MATLAB writes this out, it only wants to see the right-hand side of the equation. The left-hand side of the equation is assumed to be dy dt. So where you saw in Mathcad, you would define the whole equation, derivative and all. In MATLAB, you only use the right-hand side. So it's assuming here that dy dt equals minus 2.3y. So with that done, all I have to do now is call the solver, which is in this case is called ODE 45. As I said, that's a Runge-Kutta of, I think, 4th, 5th order is what that means. So let's see what the arguments here are. So fn is the function. That's that right there. That's the differential equation I defined. Tspan, okay, we've defined that up there. That's the range of solution. And there's the initial condition. We're going to assign those, the output, to t and y, a vector t and a vector y. Those are the vectors that define the horizontal and vertical positions on the plot. And I've got the plot right there, and I'm going to turn on the grid. So with that, there we go. Does that look right? Yeah, it looks about right. It looks just like it did before. In MATLAB, well, let's go back and fix some stuff here. Make this easier to look at. We'll turn on the property inspector. Let's slide this over there. So let's see. Let's go to line. We'll make that blue and really wide. And how about those numbers are awfully small. Let's say instead of a font size of 10, let's go to, I don't know, 20. There, now they're easier to see for you if you're on a small screen. So there's the answer. Looks great. Now there's another way to do this. Let's clear the screen here, clear the command window, clear the workspace. Now you can see down here I've got a little M file called EXMPL, for example, and there it is. What I've done here is written out a little M file. It's a function that defines the differential equation right there. Now this looks just a little different. Rather than an anonymous function, I've got this function EXMPL sub ty. So that's what ODE 4.5 is going to call. Right there, dy dt. That refers to a calculation inside the function. You can see it's highlighted right there. So whatever dy dt is, it's going to be passed out of the function. That's what this means here. Now notice I have y sub 1. What does that mean? Well, it's assuming y is a vector of variables. Now this is general. It doesn't necessarily know or care that there's only one element in the vector of variables, but there's only one. There it is. Let's go see what these warnings are over here. I think it's guessing wrong there. Okay, so the other way to use ODE 4.5 is rather than use an anonymous function, is go ahead and call this function EXMPL. So let's recall those other commands. So there's tspan, got it. There's my initial condition. Now, I'm going to make one change here. Make that at EXMPL. And let's see if that works. And there it is, just as before. Now let's change a few things here. Under that plot command, let's grab that. And just to remind you how this works, let's assign some parameters right inside the plot command. So I put B in single quotes, and that's going to make the curve blue. And I want to make it bigger, so I'm going to do this. I'm going to use another parameter called line width. Spell it right. And I was using 2 before. And turn the grid on. Right, so let's try this again. Yeah, there we go. That's looking better. Now, does that look like exactly the same curve we had before? You bet. Let's try one more thing. Let's make this 1.1 like we tried earlier. Pull that up. And let's add this in there. And hit return. And there we go. You can see the curvature changed just as it did in Mathcad. So there we go. Let's review how we did this. There were 2 different ways to call ODE 4.5. The first was to use an anonymous function. Let me clear some stuff out here for you. And let's do that. So I can either define the differential equation using an anonymous function and then call it. Remember this? There. I had an anonymous function fn. In fact, you can see it right there. Call it that way. Or I can write a function out with a differential equation in it and call it that way. Both work. Now the advantage of using this M file, it's a little more of a hassle to write out, but it lets you write out very complicated differential equations, including complicated systems of differential equations. It's much easier to try to write these out this way than try to pack them all into one anonymous function. So if you're looking for a guideline, use the anonymous function when the equation is simple, or if there's only 1 or 2 of them perhaps. If the system gets large, if the equation is very involved, difficult to write out, go ahead and write out an M file like you see the one on the screen here. I hope this helps, and we'll talk to you next time.